Hello everyone and welcome to the lab lecture video on fractional distillation. Okay, the beginning of this video will likely be review of fractional distillation that you learned about in the first semester organic chemistry lab. But eventually we should be going over some new topics that you may not have learned in your previous organic lab. So this is a follow-up to the biofuels experiment, and in that experiment, students ferment different carbohydrate sources and get a mixture of ethanol and water, along with various other components. After filtration, they obtain the fermentation broth, and then they take that for fractional distillation to be able to isolate the ethanol that was synthesized through the fermentation process. So this is a picture of a setup of a typical student's fractional distillation from this experiment. They use a column which contains some beads, some glass beads, and you can't see it because it's covered by the foil tent, but typical distillation setup with a fractionating column and a receiving flask to collect the ethanol and water that distills over. Okay, so once they've done their distillation, they can collect a series of fractions that contain an ethanol water mixture, and it's going to start out with more ethanol than water, and then eventually as the ethanol boils off, the fractions would be just water after that. They're going to determine the percent ethanol in each fraction by density. So while the distillation is going, students are practicing measuring an accurate density using calibrated micropipettes and an analytical balance. And an analytical balance is a much more precise balance than the normal balances that you might use in the lab. And then once they have a density for all of the fractions they collected, they go to an online conversion chart that will convert the density of an ethanol water mixture to percent ethanol by volume. And I've inserted a link here to the online conversion chart you can use when you're processing the data in the experiment. Okay, so just as a review, in last semester in Chem 231L at Miramar College, we did perform a fractional distillation. It was on a mixture of cyclohexane and toluene, which are miscible organic liquids. Their boiling points are 81 and 111 degrees Celsius, respectively. So they're about 30 degrees apart, so they need to be fractionally distilled as opposed to a simple distillation. In this experiment, we are going to be fractionally distilling a mixture of ethanol and water. Again, these are miscible liquids, and their respective boiling points are 78 and 100 degrees Celsius. So in this case, even closer together. We are going to be reviewing the principles of distillation and fractional distillation specifically, of miscible liquid mixtures, and such as cyclohexane and toluene or ethanol and water. And we're going to see the similarities and differences between distilling cyclohexane and toluene versus ethanol and water. So let's start by reviewing pure liquids. In a pure liquid, some of the more energetic molecules have enough energy to overcome the intermolecular attractions and escape from the surface to form a vapor, forming what's called a vapor pressure. The smaller the intermolecular forces, meaning the weaker the intermolecular forces between the molecules, so for example, between the two blue molecules here, the weaker those intermolecular forces, the easier it's going to be for the molecules to escape and go into the gas phase. And this will be, the easier it will be for them to escape at any particular temperature. As the temperature increases, the number of molecules having enough energy to overcome the intermolecular attractions and escape from the surface to form a vapor increases, and thus the vapor pressure increases. So this is basically just saying as you increase the temperature, the molecules have more energy. There's going to be a greater proportion of molecules that have enough energy to overcome the intermolecular forces and evaporate into the gas phase, creating a higher vapor pressure above the liquid surface. If you have a second liquid, in this case we're going to call it the red liquid, the same thing is true. At any particular temperature, a certain proportion of the molecules will have enough energy to leave the surface. And of course, as temperature increases, the proportion of those molecules will increase. So let's look at an ideal, what's called an ideal mixture of these liquids. So again, this pertains to miscible liquids. So, and immiscible liquids are different. We're not going to talk about that. We don't fractionally distill immiscible liquids, so we're going to be dealing with miscible liquids, such as cyclohexane and toluene, or ethanol and water. So if we mix those two liquids, right, now the tendency of the two different sorts of molecules to escape is unchanged, but only if it's an ideal mixture of the liquids. So what it's basically saying is, in an ideal situation, you mix the two liquids and the intermolecular attractions between the red and blue molecules are going to be the same as between two red molecules or two blue molecules. And if that's the case, the tendency to escape will be the same, right? If the intermolecular forces are the same at any given temperature, about the same proportion of molecules would have enough energy to escape. And the situation is very similar to pure liquids, right? With about half the concentration of each liquid in the vapor phase due to surface area. Okay, so you might think that the diagram shows only half as many of each molecule escaping, but the proportion of each escaping is still the same. The diagram is for a 50-50 mixture of the two liquids. That means there are only half as many of each sort of molecule on the surface as in the pure liquids. If the proportion of each escaping stays the same, only half as many will escape at any given time. So that's basically saying on average, at the surface, you'll have about 50% of the red molecules, 50% of the blue molecules. And as a result, if the same proportion are escaping as before, in the vapor phase, you're going to have the same number of molecules, but it will be a 50-50 split between the two molecules. If the blue molecules still have the same tendency to escape as before, and same thing with the red, that must mean that the intermolecular forces between two blue molecules must be exactly the same as the intermolecular forces between a blue and a red molecule, which is, again, the ideal liquid mixture that we've been talking about. If the forces were any different, then the tendency to escape would change. So the idea is that in an ideal liquid, the red and blue molecules have the exact same force of attraction acting between them as the pure liquid, meaning the blue to blue molecule and the red to red molecule. So if that was to not change, the interactions between two molecules were to not change, we should have essentially the same vapor pressure above the liquid because the tendency to escape is the same. So exactly the same thing is true of the forces between two red molecules and the forces between a blue and red. They must also be the same, otherwise the red ones would have a different tendency to escape than before. So you should be thinking about whether or not you think there are truly any ideal liquid mixtures, right? Is it likely that the intermolecular forces between two blue molecules, two red molecules, and a blue and red molecule are all exactly the same? But if you follow this logic through, the intermolecular attractions between two blue molecules, two red molecules, or a blue and a red molecule must be all exactly the same if the mixture is to be ideal. Okay, so now we get to the crux of it, right? While no mixture is perfectly ideal, mixtures like cyclohexane and toluene get close to ideal behavior. And we're going to be reviewing ideal behavior because when we get to ethanol and water, we're going to see what non-ideal behavior looks like. So basically, we have a graph here to the left, right, where vapor pressure is plotted on the y-axis, and we have the pure vapor pressure of A and the pure vapor pressure of B, right? These are not the same exact liquids, and so the vapor pressure above the pure liquid is not going to be exactly the same. But let's say, right, the vapor pressure of B is the one that has the higher vapor pressure, right? So that's going to be the one with the weaker intermolecular forces between them. So the B to B intermolecular forces are weaker than the A to A intermolecular forces. As a result, it's much easier for B to evaporate into the gas phase, or there'll be a higher proportion of molecules that have enough energy to enter the gas phase at any given temperature, and the vapor pressure above the liquid will be higher. So, and just to relate that, which we will later, again, to boiling point, compounds that have a higher vapor pressure have a lower boiling point, meaning, right, if they have a tendency to break free and can get into that gas phase easier, then their boiling point will be relatively lower. Okay, so on the x-axis, what do we have? It says mole fraction, right, going from 0% A to and 100% B, right, which is the pure B here on this y-axis, all the way to 0% B and 100% A on this y-axis. And an ideal mixture will have a straight line between the vapor pressure of B and A, and which basically says that if you mix B and A, let's say at any proportion, for example, here would be 50-50, right, then the vapor pressure should be exactly between A and B. So if you have a mixture that's 50% A and 50% B, if it was an ideal liquid mixture, right, and the tendency to escape is the same, then the boiling point will be, or the vapor pressure, excuse me, will be exactly between A and B, because you have 50% contribution from A and 50% contribution from B. So let's read what it says here. In the graph, the vapor pressure of two miscible liquids are plotted against the mole fraction of each component in the mixture. A higher vapor pressure results in a lower boiling point. So B is the component with the lower boiling point. And since we're talking about cyclohexane toluene, we're going to say that B in this case is cyclohexane. It has the lower boiling point, so it should be the one with the higher vapor pressure. And A is the component with the higher boiling point, in this case toluene. So higher boiling point again means lower vapor pressure. But look at the actual vapor pressure, right? The actual vapor pressure is different from the ideal vapor pressure, and instead can be drawn with a curve between A and B. We're going to explore that a little bit right now. So the actual vapor pressure of a mixture of miscible liquids differs from the ideal vapor pressure because the intermolecular forces holding A and B are usually weaker than A to A or B to B. The weaker intermolecular forces leads to a higher vapor pressure. So it's more likely that the intermolecular interactions between A and B are going to be weaker than between A and A or B to B, right? If you have, for example, if A is polar and B is not as polar, right? A would form a stronger attraction to another molecule of A than to B. So this is the likely situation that the intermolecular forces holding A and B together are weaker than A to A or B to B. So if the intermolecular interactions or forces are weaker, that means it's going to be easier for those molecules to enter the gas phase, which will create a higher vapor pressure than expected, right? Because intermolecular forces are not ideal like you would see with a straight line. So in reality, the actual vapor pressure of a 50-50 mixture of cyclohexane and toluene is higher than exactly halfway between pure A and pure B. But notice that the highest point on this actual vapor pressure line is still the pure vapor pressure of B, right? This is really important because this is going to be what's called a small deviation from an ideal mixture. And if the deviation is small, the mixture behaves as if it's an ideal mixture as far as distillation goes. So the point is that this line, right, the vapor pressure never exceeds the vapor pressure of pure B. Then we'll be able to potentially isolate pure B in a fractional distillation. We're going to see a situation where it is not a gentle curve, but more of an extreme curve later on when we look at ethanol and water. Let's review Raoult's law, which you may have learned about in general chemistry. Well, hopefully you did. The partial vapor pressure, of a component in a mixture is equal to the vapor pressure of the pure component at that temperature multiplied by its mole fraction in the mixture in an ideal case. So in equation form for a mixture of liquids A and B, and again, it's going to be a miscible liquid mixture, this reads the vapor pressure of A is equal to the mole fraction of A times the vapor pressure of the pure vapor pressure of A. And the actual vapor pressure of B is equal to the mole fraction of B times the actual vapor pressure of B. So in this equation, A and B, the vapor pressures created, are the partial vapor pressures of the components A and B. XA and XB are the mole fractions of A and B, the fraction of the total number of moles present, and the actual vapor pressures of A and B are the vapor pressures of the pure A and B, right? So these with the little knots, P knots, is the vapor pressure of pure A, right? And basically it's just saying, okay, if you have pure A, you're going to get a certain vapor pressure. But what if you don't? What if you mix it and now the mole fraction is only 0.5? Well, if you only have 0.5 molecules at the surface, then the vapor pressure should only be half that of what it would have been had A been pure. Same thing with B, right? Whatever molecule B is, it has a certain vapor pressure when it's pure. If we want to look at a liquid mixture, right, then we're only going to get a partial vapor pressure from B, where you multiply that by the mole fraction of B. But again, this is still in an ideal case because vapor pressure, it's not taking into account the fact that the vapor pressure actually changes when you make a liquid mixture. Not yet, anyway. So Dalton's law of partial pressures, right, which basically takes the partial pressure from A and B, adds them up to get the total pressure. So in any mixture of gases, each gas exerts its own pressure. This is called the partial pressure and is independent of the other gases present because the molecules are so far apart. Even if you took all of the other gases away, the remaining gas would still be exerting its own partial pressure. So the total vapor pressure of the mixture is then equal to the sum of the individual partial pressures. And this is called Dalton's law of partial pressures. Again, something you probably heard of in general chemistry. So let's convert the vapor pressure graph to a boiling point composition diagram. We'll start with the boiling points of pure A and B. Since A has the higher vapor pressure, that means it will have the lower boiling point. So notice how the vapor pressure of B is the higher vapor pressure. So when we're converting that to boiling point, we go ahead and make it the lower boiling point. And A having the lower vapor pressure will have the higher boiling point. Notice that the x-axis has not changed. So should we draw a straight line between the boiling point of A and boiling point of B for the boiling point of a mixture, right, according to its mole fraction? The answer is no. We should not draw a straight line because the intermolecular forces are not ideal. Instead, because the vapor pressure was a curved line, right, and curved in the sort of positive direction, right, then the boiling point will be a curved line in the negative direction, because remember that vapor pressure and boiling point are inversely related. So for mixtures A and B, you might perhaps have expected that their boiling points would form a straight line, joining the 2 points we've already got. Not so. In fact, it turns out to be a curve because the actual vapor pressure is not ideal, right? So remember that because we're going to have a higher vapor pressure above the liquid in a liquid mixture due to weaker intermolecular forces between molecules A and B, that means that that particular liquid mixture will have a lower boiling point than would be predicted if you had drawn a straight line between the boiling points of A and B. So if you're drawing this curve in your notes, take care. The boiling point of B is the lowest boiling point because the vapor pressure of B is the highest overall vapor pressure. Don't let the curve droop below that point. This will be the case with non-ideal mixtures, such as ethanol and water, and has consequences we will explore in a little bit. So basically what that's saying is if you're drawing this curved line, right, make sure that the lowest point on the y-axis is the boiling point of pure B, because that corresponded to the highest point on the vapor pressure graph. So to make this diagram really useful, we're going to add a second line. The second line is shown in pink, and it will show the composition of the vapor over the top of any particular boiling liquid or liquid mixture. So what this is saying is that at any particular liquid mixture of the two, so you're mixing A and B, could be a 50-50 mixture or some other percentage mixture. If you sample the composition of the vapor and you sample the composition, right, or mole fraction of the liquid, they're not going to be exactly the same, right? So for example, if I was to take a sample of the mixture to figure out exactly what percentage is A and what percentage is B, if I sample the gas above the liquid, we're not going to find the exact same composition above the vapor. And that's because the compound with the lower boiling point or the higher vapor pressure has an increased tendency or ability to get into the gas phase, right, because of its weaker intermolecular interactions. So it has an easier ability to get into the gas phase and will make up a higher percentage of the vapor composition as a result. So if you boil a liquid mixture, you would expect to find that the more volatile substance, remember that's the one with the lower boiling point or the higher vapor pressure, escapes to form a vapor more easily than the less volatile one. That means that in the case we've been talking about, you would expect to find a higher proportion of B, the more volatile component, in the vapor than in the liquid. Okay, so the diagram above shows what happens if you boil a particular mixture of A and B. Notice that the vapor over the top of the boiling liquid has a composition which is much richer in B, the more volatile component. If you repeat this exercise with liquid mixtures of lots of different compositions, you can plot a second curve, a vapor composition line. So basically this slide is talking about that pink line that we saw on the last slide. How is that generated, right? How do they know where and exactly how to draw that pink line? So the answer is it can be generated experimentally. So for example, you can make an infinite number of mixtures, right, where you have some percentage of A and B. So you can take a lot of different mixtures that would correspond to different points on the x-axis. So let's say you took a particular liquid mixture and you were to measure the vapor pressure or the composition of the vapor, meaning the percentage of A and B in the vapor above the liquid mixture. And what they see is it's going to be more enriched in the lower boiling or more volatile component. So at a given temperature, right, which you can see with the line, because boiling point is essentially a temperature, right? So the y-axis is really a temperature scale. So this line here corresponds to the actual composition of the vapor above the liquid when this particular liquid composition or mixture boils. So you've taken a mixture of A and B, we're not saying exactly what it is, but it's at this point on the x-axis. You heat it up until it boils, right? And you know exactly what the composition of the liquid mixture is. And when it boils, you can collect some of the vapor, right? And measure the composition of the vapor. And we'll actually find that if we draw a straight line over to this point, that the two mole fractions, the one of the liquid and the one of the gas above the liquid at its boiling point, right, that they can be graphed and we can get a series of data points. So let's say we took a different composition of the liquid, heated it up to its boiling point, measured the composition of the vapor above the liquid. We're going to see that it's not going to be the exact same as the liquid composition, but it will be more enriched in the more volatile component, B. And so at that temperature, we can make a dot, right, at the composition of the vapor above the liquid. And if we do that enough times, we eventually come up with a second curve, which is the pink curve that we can draw in. So if you boil a liquid mixture, you can find out the temperature at which it boils, right? Everybody can measure that. And the composition of the vapor above the boiling liquid. For example, you could use a gas chromatograph, take a sample of the vapor above the liquid and see its exact percentage of A and B and compare that to its exact percentage of A and B in the liquid that you boiled, right? That will give you the data to make the curve. So for example, let's say you boil a liquid mixture C1 right here, right? It will boil at temperature T1. This is this horizontal line here. It doesn't say it on the graph, but this is T1, okay, temperature 1. And the vapor over the top of the liquid will have composition C2, right? So this is the composition which corresponds to a different mole fraction of A and B than the liquid that created it that was boiled. And it will be more enriched in the more volatile component, right, which is B, so it's closer to more pure B. Suppose that you collected and condensed the vapor over the top of the boiling liquid and then reboiled it. You would now be boiling a new liquid which had composition C2. That would boil at some new temperature T2, and the vapor over the top would have a composition C3. So what it's talking about is a series of vaporization condensation cycles, also known as theoretical plates. So you take a liquid mixture at composition C1, you heat it to its boiling point, right? When it boils, it creates a vapor above the liquid. You collect that and condense it, right? If you collect that and condense it, you measure the composition or the mole fraction of A and B in that mixture, you're going to get a new composition C2. So if you take that liquid mixture, which is now more enriched in B than A, and you heat it again, it's going to have a lower boiling point, right? Temperature T2, which is this red line here. And the reason why it's going to have a lower boiling point is because it has more of B in it, right? Which B has the lower boiling point. So eventually it will boil, right? If you collect the vapor above the liquid, it's going to have composition or mole fraction, right? That's C3. And you can keep doing this, right? You could collect that, re-vaporize it, right? Again, collect or condense the vapor coming off of that mixture, and you would see that it has this new composition not labeled here. And if you do enough of these, eventually you might be able to get to pure B. So you can see now that we have a vapor which is getting quite close to being pure B. If you keep on doing this, basically heating the mixture up, condensing the vapor above the liquid, and then reboiling the liquid produced, you will eventually get pure B. This is the basis for fractional distillation. However, doing it like this would be incredibly tedious, right? Real fractionating columns automate this condensing and reboiling process. Boiling stones are used in a fractionating column. Basically, we're talking about those glass beads that are in the fractionating column. The vapor condenses on the stones. The condensed vapor is enriched in the lower boiling component. The liquid is then boiled and recondensed such that multiple vaporization condensation cycles are achieved before any distillate is collected. So the idea is a fractional distillation is in essence a series of simple distillations. If you just did one simple distillation, that's doing one vaporization condensation cycle, you could collect the liquid that distilled over and redistill it through a simple distillation, and then redistill the liquid that condensed from that distillation, and eventually you would get pure B, right? But this is too tedious, so instead you use a fractionating column. The fractionating column has beads or some other surface inside of it, which will provide a surface for the vapor to condense on. Because as it moves up the column, right, it will reach a cold spot where the vapors haven't reached yet, and the vapor will condense on those particular beads. Of course, from that point, it will start to fall back down the column and potentially reach back into the, the liquid that's being distilled. However, at the same time, more vapors are shooting up the fractionating column, and they give those molecules energy, and then they keep moving up the column that way. Okay, so this is another picture of a fractionating column, right? So it's this glass beads that are packing the fractionating column that provides the surface for the vapor to condense on. That condensate is enriched in the lower boiling component. If it is able to boil from that point again and condense higher, it will be even more enriched in the lower boiling component. And if we have enough vaporization condensation cycles inside the fractionating column, eventually it's theoretically possible for pure B to come out and be collected at the end of the fractional distillation. All right, so let's relate what happens to the fractionating column to the phase diagram. So suppose you boil a mixture with composition C1 here, right? The vapor over the top of the boiling liquid will again be richer in the more volatile component and will have composition C2. That vapor now starts to travel up the fractionating column. Eventually, it will reach a height in the column where the temperature is low enough that it will condense to give a liquid. The composition of that liquid will be C2. So what happens to that liquid now? It will start to trickle down the column where it will meet new hot vapor that is rising up the column. That will cause the already condensed vapor to reboil. So doesn't trickle all the way back down because of the hot vapor that is coming up to meet it. And that's critical. Otherwise, we would not get multiple vaporization condensation cycles in the fractionating column. Some of the liquid of composition C2 will boil to give a vapor of composition C3. This new vapor will again move further up the fractionating column until it gets to a temperature where it can condense. The whole process repeats itself. And hopefully you get enough of those vaporization condensation cycles happening in a column, and that can depend on the column height to eventually get pure B. That can also depend on the difference in boiling points between the liquids used for A and B. So let's start talking about what happens in a non-ideal case, right? And really we talked about how every case is not ideal. There is no such thing as an ideal mixture of liquids, right? The intermolecular forces will vary to some extent between A and A, B and B, and A and B. But some don't deviate enough to matter when it comes to fractional distillation. So we're going to start with the phase diagrams for non-ideal mixtures of liquids and introduce the idea of an azeotropic mixture, also known as an azeotrope or constant boiling mixture. So that's the goal for the next few slides. So recall that because of Raoult's law, if you plot the vapor pressure of an ideal mixture of two liquids against their composition, you get a straight graph like this. In this case, pure A has the higher vapor pressure, and so is the more volatile component. So notice that they switched A and B, right? Prior to this, A was the component with the lower vapor pressure, and B was the component with the higher vapor pressure. They just switched that just so you don't get too used to one of them having to be the higher vapor pressure and the other letter having to be the lower vapor pressure. Again, it's anything could be A and anything could be B, so don't get too bothered by that, hopefully. So remember that Raoult's law only works for ideal mixtures. In these, the forces, meaning the intermolecular forces, between the particles in the mixture are exactly the same as those in the pure liquids. The tendency for the particles to escape is the same in the mixture as in the pure liquids, right? That is not going to be true in an extreme way with non-ideal mixtures. It's not true for any mixture, but again, some mixtures are close enough to the ideal that it doesn't matter. In the case like ethanol and water, it's an extreme deviation from ideal mixtures due to extreme differences in intermolecular forces between A and B compared to A and B and B. Okay, so in mixtures showing a positive deviation from Raoult's law, the vapor pressure of the mixture is always higher than you would expect from an ideal mixture. When we were talking about cyclohexane and toluene, that was a positive deviation, right? And the vapor pressure curve was actually a little bit higher than the ideal case. The deviation can be small, in which case the straight line in the graph turns into a slight curve, right? That was the case we saw before. Notice that the highest vapor pressure anywhere is still the vapor pressure of pure A, because in this case, again, pure A is the component that has the higher vapor pressure. Cases like this, where the deviation is small, behave just like ideal mixtures as far as distillation is concerned. But some liquid mixtures have very large positive deviations from Raoult's law. And in these cases, the curve becomes very distorted. So notice how the actual vapor pressure, let's say in a mixture of A and B, is not just a slight deviation from ideal, but now it's a large deviation. What would cause that? Basically, it means that when you mix A and B, the intermolecular forces that result from A and B are significantly weaker than between A and A or B and B. That would cause this kind of very significant curve. So notice that mixtures over a range of compositions have a higher vapor pressure than either pure liquid. The maximum vapor pressure is no longer that of one of the pure liquids. So they drew this, and it's obvious it's not drawn to perfection. Okay? It's not drawn perfectly. However, it's supposed to show you that the vapor pressure of pure A is not the highest vapor pressure possible. So it's possible that some percentage of A and B in a mixture has a higher vapor pressure, right, than that of pure A. Let's explain these deviations. So the fact that the vapor pressure is higher than ideal in these mixtures means that molecules are breaking away more easily than they do in the pure liquids, right? Why would they break away more easily than they would in the pure liquids? Because the blue and red intermolecular forces are significantly weaker than the blue to blue and red to red. So that is because the intermolecular forces between molecules in A and B are less than they are in pure liquids. You can see when you mix, you can actually visualize this or measure this when you mix the liquids. Less heat is evolved when new attractions are set up. When the new attractions that are set up, that does not seem to make sense. Less heat is evolved when the new attractions are set up than was absorbed to break the original ones. Basically, it's talking about when you make a liquid mixture, if you think about the enthalpy involved, you have to break the attractions between the liquid, the molecules that are identical, so the blue to blue and red to red, and that takes energy to break those attractions. And then you get energy back when you make new attractions between blue and red, right? But what happens if you have to supply a lot more energy to break the attractions between blue to blue and red to red, then you get back when you make new attractions, right, between red and blue. You get a situation that is endothermic, right? Meaning that more heat is supplied from the surroundings than you get back, and overall the temperature goes down. And that's what happens when you mix ethanol and water. So the classic example of a mixture of this kind is ethanol and water. This produces a highly distorted curve with a maximum vapor pressure being that of a mixture containing 95.6% of ethanol by mass. So that would make about 4.4% water in that particular mixture. So this is not a very good graph, but the idea is the point at which you would measure the highest vapor pressure, right, of any particular composition on the x-axis is not that of pure ethanol, right? Instead, it's a mixture of ethanol and water where it's at 95.6% ethanol by mass. So it's actually very close, right? It's not here, it's more like over here. They just haven't drawn this distorted curve very well, right? Because it's 95.6% ethanol. Ethanol in this case is A because it has the higher vapor pressure compared to water, because it has the lower boiling point compared to water. So the highest vapor pressure actually corresponds to 95.6% ethanol. So that's like here, somewhere here on the graph, which would be over here. So it would look somewhat more like this, right, than it's actually drawn. But that was the best graph I could find. So if a mixture has a high vapor pressure, it means that it will have a low boiling point, right? Because remember that those are inversely related. The boiling point composition curve will have a minimum value lower than the boiling points of A or B. Remember in this particular example, A is ethanol, right? B is water, okay? So the green over here, water, right? 100 degrees Celsius for the boiling point makes sense. And then over here on this other y-axis, 100% ethanol, the boiling point of that is 78.5 degrees Celsius, right? But the boiling point of a mixture that contains 95.6% ethanol and 4.4% water is actually, the boiling point of that liquid mixture is lower than the boiling point of pure ethanol. So that's going to be have an important consequence as it comes to being able to separate them by fractional distillation. So in the case of mixtures of ethanol and water, this minimum occurs with 95.6% by mass of ethanol in the mixture. The boiling point of this mixture is 78.2 compared to the boiling point of pure ethanol at 78.5 and water at 100 degrees Celsius. And you might not think that the 0.3 degrees Celsius is going to make much difference, but it actually does, because it means that if you have any liquid mixture of ethanol and water that starts off with a lower percentage of ethanol than 95.6%, that when you fractionally distill, the maximum percentage of ethanol you can get in the distillate is 95.6%, which means it's impossible to completely purify ethanol from water using a fractional distillation, right? You will never get pure ethanol distilling over from a mixture of ethanol and water using any sort of distillation, including a fractional distillation, right? And that's because it never goes beyond this particular point to get to 100% pure ethanol. Because once you reach that point, the liquid and vapor, the composition of the vapor above the liquid is exactly the same, right? And so when you boil it, it will just condense at the exact same percentage of ethanol and water than you started out with a liquid mixture, so there's no way to separate it further than that. Okay, so suppose you're going to distill a mixture of ethanol and water with composition C1, as shown in this diagram over here. It will boil at a temperature given by the liquid curve and produce a vapor with composition C2. So you're starting out with a liquid mixture of around C1. You heat it up to its boiling point. You condense the vapor above the liquid. It has composition C2. If you were to distill that, right, you would create another theoretical plate, and you would distill mixture C2, and it would keep going, and you would collect the vapor above the liquid, and it would have composition C3, and so on. And eventually it reaches this point, right, at 95%, 0.6% ethanol, and cannot go any further. So when that vapor condenses, it will of course still have the composition C2. If you reboil that, it will produce a new vapor with composition C3. You can see that if you carried on with this boiling, condensing, reboiling sequence, you would eventually end up with a vapor with a composition of 95.6% ethanol. If you condense that, you would get a liquid with 95.6% ethanol. So the liquid curve and the vapor curve meet at the same point. The vapor produced will above that liquid when you boil it will have the same composition of 95.6% ethanol. If you condense it again, it will have the same composition. You have hit a barrier. It is impossible to get pure ethanol by distilling any mixture of ethanol and water containing less than 95.6% ethanol. So this particular mixture of ethanol water boils as if it were a pure liquid, right? So that's the idea, is this point here boils as if it is a pure liquid because the vapor above the liquid is the exact same composition. It has a constant boiling point, and the vapor composition is exactly the same as the liquid. So it is known as a constant boiling mixture, an azeotropic mixture, or simply an azeotrope. So bottom line, you can't get pure ethanol in a fractional distillation with water. So for example, if a student was doing their fractional distillation and they collected a fraction and measured a density, and the density was 100% ethanol and matched exactly the density of pure ethanol in the fraction, that means that that data is probably an error, right? So it has something to do with an improper measurement of the density, because it's impossible, right, to get pure ethanol in a fractional distillation with water. So if you measure a density that equals exactly to the density of ethanol, then it's an error, okay? So then the student just didn't measure the density accurately. So the liquid collected by condensing the vapor from the top of the fractionating column cannot be pure ethanol. The best you can produce by fractional distillation alone is 95.6% ethanol. What you can get eventually in the distillation, although it isn't very useful, from the mixture is pure water, right? So as the ethanol boils off, so the first few fractions will have a very high percentage of ethanol, up to 95.6%. And then eventually the fractions collected will have a lower percentage ethanol and a higher percentage water. Eventually all the ethanol will have distilled over, and left in the pot that's being heated is, or the distillation flask, is just pure water. So eventually pure water would distill and you would get a density of exactly 1. At that point, I always tell students it's time to stop your collection of fractions because you're only collecting water. And the goal is not to distill water, it's to separate and figure out exactly how much ethanol was produced in the fermentation. Okay, that's it. That's the theory behind fractional distillation and azeotropes, or constant boiling liquids. I hope to see you guys in office hours this week.